Let's explore C++ Lambda Expressions, a powerful feature for creating anonymous functions using modern C++ syntax. Lambda expressions allow you to define functions inline, making your code more concise and readable. Here's a basic example of a lambda expression. We declare a variable greet and assign it a lambda function. This lambda takes a constant standard string reference named name as input. The lambda function returns a string, which is hello, concatenated with the provided name, and then concatenated with an exclamation mark. After defining the lambda, we call it with the argument world, and store the result in a standard string variable named message. Consequently, the variable message holds the value hello, world. Let's break down the anatomy of a lambda expression. A lambda expression consists of several key components, including the capture clause, denoted by square brackets, the parameter list, enclosed in parentheses, an optional mutable specifier, an optional return type indicated by an arrow, and the function body enclosed in curly braces. Here's the general structure. Capture indicated by square brackets, parameters indicated by parentheses, the mutable keyword, the no-except keyword, return type indicated by arrow and the return type, and then the function body inside curly braces. Here's an example with all components. A capture x within square brackets, a parameter int y inside parentheses, the mutable keyword, then the return type indicated by arrow and the return type int. The function body returns x plus y. The capture clause determines which variables from the surrounding scope are accessible inside the lambda expression. Variables can be captured by value or by reference or not at all. Let's explore common capture methods. An empty capture clause, indicated by empty square brackets, captures nothing. Equals sign captures all variables by value and captures all variables by reference. X, Y captures X and Y by value, and X and Y captures X and Y by reference. Equals and X captures all variables by value except X, which is captured by reference. Let's look at the example code. We initialize an integer x to 10 and an integer to 20. In the capture by value example, the lambda function captures x by value. Inside the lambda it returns x times 2, which is 10 times 2. For capture by reference example, the lambda captures x by reference. Inside the lambda, it modifies the original x to 30, and then returns the modified value. Lambdas are particularly useful when combined with standard algorithms. They provide a concise way to define custom operations directly within algorithm calls. Here is the code. We create a standard vector of integers called numbers, and initialize it with values from 1 to 10. To find the first even number in the vector, we use the standard find-if algorithm with a lambda expression. The lambda takes an integer n as input and returns whether n modulo 2 is equal to 0. To transform all numbers in the vector by multiplying each by 2, we use the standard transform algorithm with a lambda expression. The lambda takes an integer n as input and returns n times 2. By default, variables captured by value in a lambda expression are treated as constant within the lambda's body. The mutable keyword allows you to modify these captured values inside the lambda. It is important to note that only the lambda's copy of the variable is affected, not the original variable outside the lambda. The mutable keyword is useful for maintaining state between calls to the lambda. Let's look at the code example. We initialize an integer variable counter to 0. The lambda function increment captures counter by value and is declared mutable. Inside the lambda, it increments the captured copy of counter and returns the increment value. The standard cout statement calls increment twice, printing 1 and then 2. Finally, we print the original counter, which remains 0 because the mutable lambda only modifies its captured copy. Generic lambdas, introduced in C++ 14, enhance lambda expressions by allowing the use of auto-parameters. This feature enables lambdas to work with different types without explicitly specifying them. Let's look at the code example. We define a generic lambda named multiply that takes two autoparameters, a and b. The lambda returns the result of a multiplied by b. We can use this lambda with different types such as integer times integer, double times double, and integer times double. This is equivalent to a template function as shown in the code. We define a template function called multiply_func that takes two template type arguments, ta and ub. The template function returns the result of a multiplied by b. C++14 and C++17 introduced several enhancements to Lambda Captures, providing more flexibility and control over how variables are captured. Some of the modern capture features include init captures, move captures capturing this pointer, and implicit this capture. Let's look at the code example. In the init captures example, we create a unique pointer of integer with value 10 using the standard makeUnique function and name it ptr. Then we create a lambda function that captures value which is initialized by moving the unique pointer ptr. The lambda returns the dereferenced value. In the capturing this example, we create a structure called counter, with the data member value initialized to 0. The member function getCounter returns a lambda function. This lambda captures the structures, this pointer, and returns the value. C++20 brings further enhancements to lambda expressions, including template lambdas, default parameters in lambdas, and capturing structured bindings. Let's look at the code example. The template lambdas example defines a lambda that is a template that takes a template type parameter t as an argument and returns value times 2. Default parameters in lambdas are shown in this example. We define a lambda called greet, which takes a standard string called name with the default value of guest. The lambda returns hello, concatenated with name. Capturing structured bindings example. We create a pair of integers x and y with values 1 and 2. We capture the structured bindings using auto. The lambda expression captures all variables by value and returns x plus y. Lambdas are most effective when used judiciously. They are well suited for short, one-off functions, algorithm customization, callbacks and event handlers, deferred execution, and encapsulating local state. Let's review the code example. We create a vector of integers called nums with values 1, 2, 3, 4, and 5. Then we call standard sort. We provide a custom criteria using a lambda expression. The lambda takes two integers a and b. The lambda function returns the absolute value of a less than the absolute value of b. For concise transformation, we call standard transform on nums. The lambda expression captures the integer n and returns n times n. Lambda expressions find extensive use in various real-world scenarios, including event handling and data processing. In the user interface button click handler example, we call the setOnClickListener method on a button. We pass a lambda expression as an argument. The lambda captures this pointer. Inside the lambda expression, we call the update user interface function and then call the log event function with the message button clicked. For data processing example, the code filters and transforms data. We call standard ranges views filter, passing in data and a lambda expression. The lambda captures the item and returns true if the item value is greater than 10. Then we call standard ranges views transform. We pass a lambda expression as an argument. This lambda captures the item and returns the item name. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.